Chapter 8, Section 3, LU Decomposition. LU decomposition is a method that enables us to solve systems of linear equations efficiently. In this section, we will explore what LU decomposition is, why it is efficient. Also, this section will demonstrate a practical example of how LU decomposition is applied to systems of linear equation. LU decomposition is frequently used to solve systems of linear equations. So, what is LU decomposition? LU decomposition is a matrix factorization technique that breaks down the square matrix into the product of lower triangular matrix and upper triangular matrix. LU stands for lower and upper, referring to two specific types of matrices that we create from a given matrix. Essentially, LU decomposition enables us to break down a square matrix into two simpler matrices. In the context of LU decomposition, L represents the lower triangular matrix, and U represents the upper triangular matrix. The lower triangular matrix, L, is a matrix where all the entries above the diagonal are 0. The upper triangular matrix, U, has all elements below the diagonal equals to 0. In terms of equations, LU decomposition expresses the matrix A as the product of two simpler matrices. A equals LU. This means that instead of directly working with matrix A, we can work with L and U, which can be much easier to manipulate. Let's see how LU decomposition simplifies the process of solving systems of linear equations. Let's say we need to solve a system of equations of this form: AX equals B. Here, A is a square matrix, X is the vector of unknowns, and B is a vector. By decomposing A into L and U, the system becomes two simpler systems. Solve for y in the equation Ly equals B using forward substitution. Solve for x in the equation Ux equals y using back substitution. This process can make solving large systems of linear equations much more efficient, particularly when you need to solve the same system for different vectors B. Now, let's move on to the example. Let's use this system of linear equations to demonstrate how we can apply LU decomposition to solve for unknown variables. These three equations represent a system with three variables, x1, x2, and x3. Our goal is to solve for these three unknowns. We can write this system in matrix form, where A is the coefficient matrix, X is the column vector of unknowns, and B is the column vector of constants. So, let's write it out explicitly. The matrix A contains the coefficients of variables in the system. The vector X represents the unknowns we want to solve for, and B is the vector of constants. Now, let's go on to these three steps. The first step is LU decomposition of matrix A. As I mentioned earlier, LU decomposition expresses the matrix A as the product of two matrices, A equals LU, where L is a lower triangular matrix, and U is an upper triangular matrix. We have already known each element of the matrix A. As I mentioned, A equals the product of L and U. The matrix L can be expressed in this way. It is a lower triangular matrix with ones on the diagonal and the other elements being the coefficients of the row operations. To make the computation simpler, we set the diagonal elements to 1. The matrix U can be expressed in this way. U is an upper triangular matrix. To solve for L and U, we will directly compute the elements by multiplying the matrices L and U and matching them to matrix A. Let's start with this equation. By multiplying the two matrices L and U, we can obtain this matrix. Since this matrix equals the matrix A, we can obtain the values of the first row. So, we can obtain the values of the elements in the first row. Let's substitute these values. Repeat this process. We can find the values of all elements in the matrix L and U. Now we have obtained the values of all elements in the matrix L and the matrix U. Now that we have L and U, let's go back to this equation. Since A equals LU, we can rewrite this equation in this way. Then, express Ux as a vector y. So, we can rewrite this equation in this way. The equation of Ly equals B can be expressed in this way. We can solve this equation by forward substitution. Forward substitution is a method to solve a system of equations when the coefficient matrix is a lower triangular matrix. The process for forward substitution works as follows. Start by solving for the first variable y1 from the first equation. Then, use the computed value of y1 to solve for the second variable y2. Continue in this manner, solving for each successive variable in turn. Since the matrix L is a lower triangular, each row's equation only involves the variables that have already been calculated, making the process straightforward and sequential. We already have the matrix L and a vector B with the concrete values of all elements. So, using them, let's set up the system. Next, let's solve for each variable step by step. First, solve for y1. y1 equals 5. Next, substitute y1 equals 5 into the second equation to solve for y2. We can find that y2 equals 0. Finally, substitute y1 equals 5 and y2 equals minus 4 into the third equation to solve for y3. We can find that y3 equals 4. So, the solution for y is this vector. Now that we have solved for y in the equation Ly equals b, the next step is to solve for x by solving the equation ux equals y. Recall that y is the upper triangular matrix from our earlier decomposition. We need to solve this system using back substitution, which is a method for solving upper triangular systems. The process for backward substitution works as follows. Start by solving for the last variable xn from the last equation. Then, use the computed values of last variable to solve for the second to last variable, xn minus 1. Continue in this manner, solving for each previous variable in turn. Since the matrix U is upper triangular, each row's equation only involves the variables that have not yet been computed, making the process proceed in reverse order. Now, let's apply backward substitution to solve ux equals y. Let's set up the system of equations. Let's start with the third equation, as it only involves x3. We can find that x3 equals minus 0.8. We can substitute this value into the second equation to solve for x2. So we can find that x2 equals 0.8. Finally, we substitute x3 equals 0.8 and x2 equals 0.8 in the first equation to solve for x. We can find x1 equals 1.7. So, we have solved for x, and the solution to the system of equation is expressed by this vector x. To summarize, using LU decomposition, we first decompose matrix A into L and U, then solve the equation Ly equals B using a forward substitution, followed by solving Ux equals Y using back substitution. This gave us the final solution for x1, x2, and x3. The most important benefit of LU decomposition is its efficiency for solving multiple systems of linear equations. Once a matrix A is decomposed into its lower triangular matrix L and upper triangular matrix U, these matrices can be reused to solve multiple systems of the form Ax equals B. This is particularly useful when solving several systems with the same coefficient matrix A, as the costly factorization step is performed just once. After LU decomposition, solving each system only requires solving two triangular systems, Ly equals B and Ux equals 1. Each of these steps is computationally efficient, making it significantly faster than performing Gaussian elimination from scratch for each new system. Gaussian elimination needs to perform the entire row reduction process for every system, making it much less efficient when solving multiple systems with the same coefficient matrix. Thank you for watching. Please thumbs up and subscribe to my channel.